Hello everyone, I'm Jiazhen from Fudan University. Today I on behalf of my co-authors to present our work, Efficient Customer Incident Triage by linking with System Incidents. In this talk, I will first talk about the problem in current customer incident handling. Next, I present an empirical study as the motivation of this work. Then I introduce our approach, called LinkCM, which links customer incidents with system incidents so as to accelerate the incident triage procedure. The cloud system in Microsoft covers a wide production length, including infrastructure services, platform services, and software services. These cloud services not only directly serve end users, but also support companies in deploying their own online services. Although many efforts have been made on improving the service quality, it is inevitable that customers encounter various problems when using these services. Therefore, it is a critical task to quickly resolve the problem encountered by customers, so we can ensure customer satisfaction. In current practice, customers would report the encountered problems to the customer support team. The support engineer can successfully recover most of the customer-side errors or simple problems. However, some problems can be caused by system failures, and the support engineers cannot simply recover these problems. For these cases, the support engineer would raise customer incidents and then send these incidents to the responsible developer team for further diagnosis. However, the cloud system serves millions of customers. As a result, the same system failure may affect different customers. These customers may report the problem to different support engineers. Since the support engineers do not have strong domain knowledge about the backend system, multiple customer incidents may be raised. In addition, according to our experience in operating a large-scale cloud system, it is also hard for support engineers to send the customer incidents to the responsible developer accurately. So, these customer incidents caused by one system failure may be sent to different developers. On the other hand, large-scale cloud services typically adopt a large number of monitors to conduct automated, real-time system incident detection, and the detected incidents would alert the responsible team automatically. During the whole procedure, we can find that the same failures are tackled in redundant processes, leading to inefficiency. In the whole procedure, we can find that the redundancy is mainly caused in the customer incident triage part, considering that the monitor-reported incidents provide details for diagnosis and the corresponding team would be alerted once the incident is detected. So, instead of directly sending customer incident to the develop team, it is a more efficient way to link the customer incident to the monitor-reported incidents. For simplicity, I will use CI and MI to refer to customer incident and monitor reported incident respectively. So, to determine whether this new pipeline is feasible, we need to answer the following two questions. The first question is, can MI be reported before the CI? If not, we cannot link these incidents. The second question is, can the link help the CI handling process? If not, this work is unnecessary. Next, we present an empirical study as the motivation of this work. To answer the above questions, we first define non-customer incident, or simply KCI, as the CI whose corresponding MI is reported before it is raised. We conducted an empirical study about KCI using the historical customer incident handling data from 7 real cloud service systems in Microsoft. In the study, we investigate two aspects: the percentage of KCI among all CI, which shows how many related system incidents can be reported before the CI is raised. The second aspect is the processing efficiency of KCI, which shows the benefits of using system incident information for customer incident triage. We first investigate how many related MIs can be reported by system monitors before the CIs. The results are obtained through checking the creation time of a CI and its corresponding MI. If the MI creation time is earlier, we consider that such a customer incident is a KCI. In this figure, we can find the percentage of KCIs in the 7 studied systems ranges from 68% to 93%, indicating that the majority of corresponding system incidents can be reported by monitors before the customer incidents. Since most customer incidents are actually KCIs, next, we investigate how many KCI can be correctly detected at the start of the handling process. The results are shown in this figure. However, the results are not satisfying. On average, only about 30% of KCI can be correctly detected in current practice. The results also reflect that it is quite difficult for the support engineer to correctly triage the customer incidents. Then, we present the speed-up ratio of the triage time for detected KCI comparing with that of not detected KCI in Figure 3. For fairness, here we only compare the incidents with the same severity. The results confirm that the triage time can be greatly reduced with the help of related system incidents. According to the empirical study, we can summarize 2 findings. First, in most cases, the system incidents can be reported by system monitors before the customer reports problems. Second, the triage time of CI can be greatly reduced with the help of MI. Hence, we can conclude that linking CI with MI is a promising way to improve the efficiency of CI triage. However, linking CI and MI is not easy. One reason is that they are essentially different representations. This figure shows an example of a pair of related CI and MI. The CI is written in natural language and describes the observations from customers, while the MI consists of machine-generated content describing the anomalous issues. Although there are a lot of approaches focusing on natural language processing, field work can be reused for handling machine-generated contents, which are designed for specific systems. So, how to process the MI is thus challenging. On the other hand, considering that CI and MI are both text data, one may resort to supervised learning methods. However, there are insufficient labeled data. Manually linking CI and MI is labor-intensive and requires domain expertise. As a result, the high laboring cost makes it infeasible to directly use supervised learning methods. During the operation and maintenance of the cloud service systems, we observe that there are a lot of related system incidents reported by monitors. These associated system incidents can be treated as labeled MI to MI link data. In this regard, we have sufficient data to train an MI to MI link prediction model, and this model can learn the effective representations of MI for link prediction. Considering that our target is linking CI and MI, we can adopt transfer learning to reuse the learned MI representations to the CI and MI link prediction task. Here is the overview of our approach, called LinkCM. Given a pair of CI and MI, our approach first extracts the correspondence between CI and MI in the textual encoding part. Then, it conducts feature combination to generate more effective features. Finally, LinkCM uses a simple binary classification model to predict whether the given CI and MI are related. The textual encoding part is used to extract the relation between CI and MI. We first use 2 different encoders to extract the word embeddings from CI and MI. Specifically, CI is written in natural language, and there exist a lot of pre-trained word embedding models for natural language processing. However, many terminologies about cloud systems may be treated as unknown words in commonly used corpus, So, directly use existing pre-trained models is infeasible. Here, we fine-tune the BERT model with extra corpus containing the cloud terminologies about our system. For the MI encoder, we directly use a single word embedding layer whose weights would be learned from the other model in the transfer learning phase, which will be introduced later. Then, we use a decomposable attention model to extract the word-level correspondence between the word embeddings of CI and MI. Unlike common attention mechanism, the decomposable attention model takes two word embeddings as inputs, conducts attention between the words, and generates two representations of correspondence between the inputs. As a result, the output representations V1 and V2 are suitable for inferring whether the CI and MI are related. We further combine the extracted vectors V1 and V2 from the textual encoding part to generate effective features for classification. Specifically, we use the operators including add, multiply, absolute value of subtraction, and concatenation. The four generated features are concatenated together as the final feature used for classification. Finally, we use a fully connected neural network to predict whether the CI and MI are related. So, another problem is how to train this model. As introduced before, there are limited labeled data. Directly train this model cannot achieve good performance. So, we propose a transfer learning-based strategy. We first train a symmetric model with a similar structure to the original one. There are two main differences. First, the symmetric model takes two MIs as inputs, so it only uses one MI encoder to process the inputs. Second, the symmetric model does not use the concatenation operator, because it may produce inconsistent results. And in the training phase, we first use the associated MIs to train the symmetric model. Then the weight of the textual encoding part is transferred to the original one. Finally, we use the correlated CI and MI data to fine-tune the decomposable attention model and train the classification part. To evaluate the effectiveness of our approach, we compare the performance with its two variants. Variant 1 is constructed by removing the transfer learning strategy. For variant 2, we use TextCNN as the MI encoder. This variant also adopts transfer learning. The results are shown in the table, and our approach achieves the highest F1 score for all datasets. Specifically, it outperforms variant 1 in terms of all three metrics. The results prove the effectiveness of the transfer learning strategy. On the other hand, the recall of our approach is a little worse than variant 2, while our approach performs much better in precision. These results prove the effectiveness of the MI encoder. We further use two representative cases to show the benefits of adopting our model in industrial practice. The first case is API-related issues. Typically, API failures are caused by system fluctuations and would be automatically repaired. Hence, the MI has low severity, and the developer did not investigate each single API failures, since it is difficult for them to judge which API failure would impact customers. However, in this case, customers were affected, and it may take several hours to assign the CI to the responsible team. Our approach can link such CI and MI in several seconds, and allows the back-end developer to perceive customer-side problems and help prioritize the mitigation of CI-related failures. According to our estimation, it can reduce 40% of CI mitigation time. The second case happened when an outage occurred on the cloud search service. Many customers reported the service errors. However, the developers were working on the outage handling. After fixing the outage, the developers could have time to handle the CIs and notify customers. With the instant links, the CI can be automatically fixed once the outage was fixed. So, using our approach can help achieve quick response to customers and reduce redundant workloads. In this case, according to our estimation, our approach can help save 30% of CI response time. Finally, I discuss the adaptability of our approach. First, the whole framework of LinkCM is applicable to cloud service systems from other companies. It requires system corpus, historical customer incident and system incidents to employ our approach, which is general and common for large-scale cloud systems. Second, if the service system extends in scale, our approach can be directly adopted. As for a brand new system, it requires a certain amount of data to fine-tune our approach. In conclusion, in this work, we conducted an empirical study to show that linking CI with MI is a promising way to accelerate the CI triage. And we propose a transfer learning-based approach to predict whether the given CI and MI are related. Experiments prove the effectiveness of our approach, and the representative cases show the practical benefits of linking CI and MI in industrial practice. More details about this work can be referred in our paper. And welcome to discuss. Thank you.